and also the building frames, and the rest of the session is your about the assignments and general discussion, feedback, or all kind of questions from you will be answered here in the next hours. Okay, let us see that next what is there in that. I'll show you quickly the slides. So, introduction to the influence lines diagrams, and then let us see the, yes, this is for the reactions for the influence line, it looks like this. Then for the yes, to finding the values, and then next is that the shear, for the shear it looks like this. Next is for bending moment, it looks like this. So, this is day 1 session 1, and next day 1 session 2. So, if it is day 1 session 2, yes. So, value of the function, we have seen that at how to find out the value of the function for actually concentrated load and uniformly distributed load. Just 1 minute, one thing you can just recapitulate that for uniformly distributed load, I am drawing the influence line diagram for a unit load which is a concentrated load. So, it may appear that I need to draw a separate influence line diagram for uniformly distributed. No, the influence line diagram is the same. For uniformly distributed load, I will integrate over the area where it is occupied the influence line diagram. The load is the occupancy of the load within that diagram. So, there is no need for any more diagram. The one diagram is sufficient. Next is the qualitative influence line, the Muller-Varilov principle. You know that if we remove the action and then put back, then how it actually deflects, it actually gives the qualitative shape of the influence line. So, you can see for reaction the influence line exactly matches the shear and for the bending moments. And then day 2 session 1. So, session 3, day 2 session 3, we have the concentrated load effects. Go, yes please, just 3 concentrated loads we have taken as example from Professor Hibbeler's book, and then we have seen that for shear how to determine the maximum at a point. It depends upon, there are several possibilities we need to explore and then finalize, or else, yes, or else we need to observe the functional changes, and when the changes become negative, we actually understand the earlier one was better. Yes, go ahead. Yes. So, these are the functional changes and the slopes, and then slope of the curves we actually track, and from there we understand that which one was the best for increasing the function. Yes. Now, for the bending moment similarly we have drawn, I have not elaborated this, it is kept as your homework, probably you have done that and you have understood that it can be extended to your bending moment. Now, for the UDL larger than the span, this is how it works, and if there is any confusion, how can a load be larger than the span? A train is moving on the track and there is a small bridge. So, the most of the train is actually on the ground and some portion is on the bridge. We are talking about exactly that, and we are not interested to know right now what happens when the load is directly transferred to the ground, and we are only concentrating on a train of load fully occupied onto the bridge. Next is the UDL shorter than the span. It is a case of a longer bridge with a shorter vehicle like a truck moving onto the bridge, and we are examining what is the effect, and we have seen, yes please, the conclusion. Let us see once again. Yeah, please stick to this. Bending moment at a section will be maximum when the uniformly distributed load is so placed that the section divides the load in the same ratio as it divides the span. Please remember this and you can solve a lot of problems for statically determinate bridges. Absolute maximum shear and moment we have actually tried to determine. Yes please, and then we have seen that they are dependent upon the support conditions, and for some support condition it is easy to just understand the maximum the loads where it should be placed, and some we need to do some computation. Yes please, next slide. Yes, we have also seen that one of the load should be equidistant from the geometric center line from its resultant, the sum total of all the forces as a resultant. So, they should be equidistant, and that is the position which can make it maximum, but you need to investigate it for other loads if there are trains of loads. Yes please, next we have a problem solved. Yes, this is the conclusion. So, we have a problem solved from Professor Menon's book, and you can see that the red line, you can see the red line, show with the cursor, the red line, from there the resultant and one of the force is kept equidistant, and then we will examine this case as one of the potential candidate for maximum bending moment there. Maybe the other things we have to do that with 150 load and others. So, we do the computations and then shown that it was really the maximum. So, that ends the session 3, and in session 4, yesterday the fourth session we have seen that the influence line diagram for determinate trusses, and you may understand that the trusses are not directly loaded, is on the floor, the vehicle is on the floor. So, the load transfer is from the longitudinal girder or the stringer beam to the cross girders or the cross beams to the nodes of the trusses, and there are two plane trusses on both sides, and we are drawing the influence line diagram for the member forces of the trusses. That is the action the members of the trusses are subjected into. Now, next is that, yes, so it is basically a truss solution with unit load at different joints, and the load moves on the bottom chord, and that is one of the example for the truss. Yes, please. I think there is nothing basic, but we have solved probably one problem. Yeah, this is the shape of the influence line diagram for the truss, and we have also shown that the Mueller-Breslau principle is equally applicable for truss. You destroy its axial force carrying capacity and try to actually keep it overlap within the member by force, and the shape it takes, the nodes, the movement of the nodes, if they are followed, they will describe the actually the qualitative shape of the influence line diagram. So, let us see that how it works for using the Mueller-Breslau principle. Yes, this is how the green distortion shows that the movement of the nodes, and the red lines show the qualitative influence line diagram for the member forces into the truss. Yes, please. I think we have concluded with 4 sessions how to draw the influence line for point loads, how to extend it to uniformly distributed load, but we have always restricted them to the statically indeterminate structures. So, today is the day, it is 3 session 5, we will actually extend the idea to influence line diagrams for indeterminate structures. While doing that, we may need to discuss something as a background or prerequisite for this study, that statically indeterminate structures are those which have either more number of supports or more number of members than is necessary to maintain static equilibrium. In fact, the more number of supports, it gives rise to external indeterminacy. So, a structure can be internally determinate, but externally indeterminate. Other way around, a structure can be internally indeterminate, but externally indeterminate. That means, you may sometimes be able to solve the reaction forces, but not the member forces of the truss or internal stress resultants, or you may be able to solve for the internal stress resultants or the member forces, but not the external reactions. So, or sometimes they are both, that you can neither solve for the external reactions, neither you can solve for the your internal stress resultant, unless there is a specific information obtained from the deformation of the structure. So, this is statical indeterminacy. Just to, I have shown you on the first day. So, we can find out the indeterminacy of the structure from the beams for the trusses using this formula. You will get similar, if not exactly written in this form, the similar formula in all books. This is for the beam type of structures, this is for 2D truss structures, this is for 2D frame structures, and the number of unknowns and number of knowns determine the form of the equation you can easily form yourself. And it can be extended to 3D truss and 3D frame as well, and these are all for the actually the skeletal structures or slender structures, which are one of the dimension is much more than the other, either it is the beam or the member of the trusses. They are all slender structures. If not, a structure can also be actually statically determinate or indeterminate, and as well as a complete 3D entity. So, that we are not discussing, just I will show you some of the examples for statically indeterminacy, determination of statical indeterminacy. You look at it, that suppose you are given a beam like this, and you need to find out the statically, whether it is statically indeterminate or determinate. This is statically determinate and the calculation shows like that, but later on you will find that instead of calculating, you can actually find out by observation whether it looks fine or if it looks stable, as well as just the required number of supports are there and no more, that you can really find out. So, each can be extended to frame type of structures and their statical indeterminacies can be found out either by formula or by observation. So, you can do it by observation, like you see that you can just mentally cut those structures into to make it statically determinate, and then the number of cuts you made, the number of release of the internal stress resultants or the reactions will actually tell you the redundancies. Now, one more thing about the stability, statically determinate or indeterminate, from the calculation it will not immediately or automatically imply that the structure is stable. Stability is, of course, from the calculation there is an indication that the structure is stable or not, but you need to carefully examine the support conditions or internal arrangement into the structures to be sure that a mechanism cannot form due to the loading. For example, so even if the calculation shows that this type of structures where there are 3 rollers are actually, as per the calculation, they are stable, or a beam is actually sitting on 3 rollers, as per the calculation they are maybe stable, but still they may not be actually statically, they may not be unstable, it appears to be stable, but it is not. And also, even the equation is satisfied, even if they are found to be statically determinate, the question of finding out that determinacy does not arise if the structure is unstable. I hope you will take care while actually studying the statically determinate structures and statically indeterminate structures. First, the stability of the structures from the calculation as well as from observation, and then go ahead with the determination of the indeterminacy. Let us now focus on to what is there into our PPT for the influence line diagrams for indeterminate structures. That I have told you that statically indeterminate structures, how they are those which have either more number of supports or more number of members than is necessary to maintain static equilibrium. It has been observed while dealing with the influence lines for statically determinate structures that it is necessary to solve static equilibrium equations for part of structures cut by section at appropriate locations to obtain the external reaction or internal stress resultants, that is the bending moment, etc. We have done that for statically determinate structure. Now, the above approach, which was very easy for us for statically determinate structures, will become much more tedious and involved while dealing with statically indeterminate structures because of the redundancies. So, if this is a redundant, finding out the deflections and others will be a challenging task. And so, the Muller-Breslau principle, which is equally applicable for indeterminate structures, may be used conveniently as that. So, you just understand that your basic approach was that you will solve a static equilibrium problem for the structures which was cut and separate rigid bodies we have considered, and find out either the reactions or the bending moments or the shear force as a unit load moves from one side to the other for each location, either by tabulating the values or forming the equations. That is our approach. This approach, if you apply to statically indeterminate structures, there are the solution for the actually the member forces or the stress resultants for statically indeterminate structures. You know, there are 2 ways. One is the force method, the displacement methods, where the forces are taken as unknowns or the displacements are taken as unknowns, but ultimately you need to remove the redundant, solve for the determinate structures, then come back with the compatibility equation or the equilibrium equation, whatever the case may be, either it is the force method or stiffness method, and then you get a solution for the stress resultants or the external reactions, whatever it is. So, it's a tedious task for the statically indeterminate structures. Rather, let us examine that if there is a somewhat convenient way using the Muller-Breslau principle. So, the Muller-Breslau principle, which is equally applicable for indeterminate structures, may be used conveniently to determine the influence line diagrams for indeterminate structures as the influence line for external reaction or internal stress resultants, as for example bending moment in a structure, may be obtained qualitatively to some scale by moving the same force through a small distance or rotation. If we apply this to a statically indeterminate structure, let us start with an indeterminacy of 1 for explanation. For the indeterminacy of 2, you need to remove 2 redundant forces to have and apply back to see the displacements of the structure. Let us now examine with a single redundant force and clear our mind how it is applicable to statically indeterminate structure. So, I have taken this from the book The Methodology from Professor A.K. Jain's book, because many of the books does not discuss about the indeterminate structure, some of the books discuss, and especially Professor Wang's book, and they discuss about the indeterminate structures. So, now coming to that, so not many books you will get dealing with the indeterminate structures really, but since why we will actually be why the question arises, why we should be after the indeterminate structures. The thing is that in civil engineering the loads are very uncertain, the failure of a structure is fatal and catastrophic. So, almost none of the structure, unless that what is the basic difference between statically determinate structures and statically indeterminate structures? The indeterminate structures have many more members to share the loads in case 1 or 2 fails or become ineffective. That is the advantage. The disadvantage is that since there are extra member forces, then what is needed for static equilibrium of the structures, then these structures are actually affected due to the secondary stresses developed, suppose due to the heating, the differential heating onto the structure, the temperature changes, the lack of fit into the structure if one member is shorter than required, but it is forcefully fit, or there is a support settlement in a structure. The structures which are indeterminate will be heavily affected, but the determinate structures may actually be not affected due to that. For example, on the alluvial soils, if the bridges are constructed and the bridge pier and the bridge decks are made statically determinate by separate span, then if the pier settles a little bit, then there won't be any moment induced into the spans. There will be uncomfortability into its operation due to the subsidence, but it will not be a huge moment which can break the structure actually. So, it will be judicious to use a statically determinate structure there, but most of our structures from the buildings frames to others will be highly indeterminate. That is why it is needed to study statically indeterminate structures and have a thorough knowledge how to deal with that. I hope in other coursework you will be learning about the force method and the displacement method, that will be very much required. Right now I am justifying why we should actually at least know how to extend the Muller-Breslau principle or the general applicability of the influence line diagram towards statically indeterminate structures. We cannot stop only at the statically determinate structures. Now, coming to our slides for the statically determinate structures, that influence line diagram for a reaction are, let us take an example. I have a continuous beam, very simple. I have one more support than needed. So, statically determinate, I know if there is a pin joint and a roller joint, what happens if a unit load moves onto it, that we know. Now, it is to be extended to a statically indeterminate structure, and if there is one more support. Now, according to Muller-Breslau principle, suppose for example, let us do the influence line diagram for the reaction R A for this continuous beam. Let us take the EI is unity for our computation. We will do real computation. Not only the Muller-Breslau principle I have so far extended only for drawing qualitative influence line diagrams for statically determinate beams and statically determinate trusses. I have never extended beyond that. I will also tell you later that for statically indeterminate trusses or highly statically indeterminate structures, the advantage of using Muller-Breslau principle may die out, because if you remove one redundant and try to examine what is the displayed shape, the other redundants will prevent it from displacing it quite well, where the actually the shape of the curve will be apparent. So, there is a disadvantage theoretically, there is a disadvantage in experimental determination of influence line diagrams. Now, coming to the point of this particular beam, the vertical restraint at support A is to be removed and a unit vertical load is applied at A. Then as per Muller-Breslau principle, the deflected shape of the released beam under the action of the unit load, if displacement is small, will to some extent to some scale represent the influence line diagram for the reaction RA. For the reaction RA, this is the influence line diagram for the reaction RA. That means, if a unit load moves from here to here, if I release this redundant force and then I say redundant force is only vertical ability, it has not released the horizontal restraint, only the vertical restraint condition is released. So, it can go vertically up and down, but cannot move sideways. And then if I apply a unit load here, if the deformation not excessive, that means I am still using the first order theory, then the deflected shape of this statically indeterminate beam will give me an idea of the qualitative influence line diagram. And if I am efficient in computing the values, I can get the quantitative the influence line diagram as well. Let us see how it is that it looks. You see that I have released the redundant, then I have put back a unit load here. So, you can see this will go up, and you can see that as if you are doing an experiment. And one confusion the students may have, that is the roller joint and the roller joint and the pin joint. It appears sometimes to the student's mind that it is as if to drum type of thing you are putting a particular beam over that. So, it can well be taken up. No, that the pin connection is, so the student thinks that the pin connection and the rollers are like this. The pin connection and the rollers are like this. It is actually not. It cannot be taken up. It cannot be taken up. It restrains the movement there. So, if so, then if you make this up, then if it is restrained here from upward movement and restrained here from upward movement in both places, then this goes up, and to have the geometric compatibility of the beam, it will take a curved shape like this. This shape, according to the Muller-Breslau principle, which could have been derived, I have not derived from our energy principle and the virtual work principle. Now, this shows the the qualitative influence line, not yet quantitative, qualitative, this one. But if you normalize, it of course gives the quantitative value also. We will see how to actually determine that. So, this is a very important and useful conclusion for us. The problem we have avoided the real issue which we were having at the first principle, that let the unit load move. I have the rigid body, your the free body is drawn, from there the solution for the different stress resultant. Those we are not doing. We are already with the Muller-Breslau principle. We have got the qualitative shape of the diagram. Now, it is left out to us to determine the quantitative values, and the problem is reduced to determining the deflections of the Zilli structure. The structure now is divided. So, this is to be determined, the deflection due to this load. How can I determine that? So, the structure is now, so there are several methods. You might be aware. Now, let me have some discussion about this. So, can you focus on me? It is reduced to find, so the redundant is released. We are with the influence line diagram for the reaction. We are with the influence line diagram for the reaction for the indeterminate beam. But what we have drawn after release and putting back the redundant, taking the redundant force as unity and a known force to us, it is reduced to determination of the deflection of a statically determinate structure. Now, how do I do that? It depends upon our methodology and the tools we have in hand. You can recollect that what we have in our preliminary studies of finding out the deformations or the deflections of structures, we have either used the equations, the moment curvature relationships and the closed form equations for the deflection and integrated twice to actually determine the deflections. That is one way, but it becomes very tedious if the EI or it varies across the sections, and also it may be much more convenient if we take help of the M by EI diagram and form either with the moment area, use the moment area theorems for finding out the slopes and deflections, or even better if we use the conjugate beam type of methods, which will be very quick. Now, I'll just discuss very briefly about the conjugate beam method, but let me point out that what are the different methodologies available. We can use the integration procedures for the moment curvature relations. You can remember that M by EI, which is the relating the moment and the flexural rigidity. EI is the flexural rigidity and M is, so I can write that M by EI. So, M by EI, it can be related to the curvature, which is d square y dx square, and then I can integrate them. So, this is the curvature, and I can integrate them and then find out the values. These are what we can do for one is the integration method. One is the integration method, or we can use better. We can use the moment area theorems. Moment area theorems. So, moment area theorems means if I draw the M by EI diagram due to, so this is the M by EI diagram for a beam, and if I load the beam with the M by EI diagram, then the slopes and deflections we can easily find out from that, the load under the curve and also the moment of that load with some point in between 2 points we can find out the slopes and deflection. And conjugate beam method will be another, conjugate beam method will relieve us from the relativistic approach of moment area theorem, where the displacement of one point is dependent upon the reference of other point. The conjugate beam method will relieve us from that. We can even go for different energy methods. Energy methods we can also use. We can use unit load method if we like. Even we can use the Castigliano's theorems and several Castigliano's theorem. You know that the total strain energy, if you have what should I write for strain energy? Okay, write in. So, with respect to a load will give the deformation del u. So, del u del p will, so del u del p will be the actually delta. So, these are the different avenues for computation of deformations, and we are actually these are the different avenues. These are the different avenues for computation. It is your choice. Now, there are convenient and inconvenient methods for different structures and loading configurations. I am so let us go to the slides. So, for this particular problem, what I did it's from the book also. The conjugate beam method is suggested. So, what I quickly just give you a brief overview of the conjugate beam method, that if you like the moment area theorem, if you load the beam with the M by EI diagram and also take care of the kinematic conditions at the supports, then you can actually convert the real beam into a beam which we will call a conjugate beam, and it will be possible that if we are interested about finding out the slope, we actually find out the shear in the conjugate beam, and these are the actually the correspondence between this. I think it is not the time to discuss in detail about the conjugate beam. You have to read in background. I am giving you the prerequisite for that. It is that the shear in the conjugate beam will be the slope of the real beam, and the moment we calculate at a section for the conjugate beam, it will give the actually the deflection at that point. So, that means we will and there are different kinematic conditions you need to follow to draw the support conditions of the conjugate beam. So, that means using the conjugate beam method, what you do, you load the real beam with the M by EI diagram, convert the support conditions into what kinematically is permissible for that conjugate beam to comply, and then you forget about the real beam. You find out the shear and the moment into the conjugate beam, and you get the slope and the deflection of the real beam. That is done here. Please see. So, I have divided the section the beam into several sections, because now that thus the problem is reduced to determining the deflection of the release structure. So, we have divided the beam because it is statically indeterminate. I am going to get the points which will not correspond to linear variations. So, I need to keep track of the nonlinear variations, and this is how I divide it. So, my entire work is now to find out the shear and bending moment into the conjugate beam, and I will find the slope and deflection. So, it is the bending moment into the conjugate beam which will give me the deflection. I am after that. This loading is the M by EI diagram of the actual loading. I have now drawn the free body. I have found out the reaction of the conjugate beam, which is from the M by EI diagram of the real beam, and I am fully ready to determine the bending moment at a section. And I think on the first day I have told you how to find out the bending moment at a section. Once again, just 2 minutes we will recapitulate how to draw the bending moment diagram. So, there is a load P, there is a load. So, this is P, suppose this is P by 2, this is P by 2. I am interested to find out the bending moment at this section. So, starting from the left end, I must suppress the right end, and I will count that what distance this load is actually acting, and then say that the moment at this section mx is actually equal to p by 2 into that distance, and like that I will go ahead for this unless I have a change, and then I can incorporate the other force which is coming. Like that you draw the bending moment diagram into a structure. Now, come to our slides, that what we are exactly doing. So, now here in the indeterminate structure we are with the statically we are with the conjugate beam method, and then it's simple. I will not discuss any more. It's simple. You just sit at a section what you have actually found out from. So, you sit here, you sit here, you sit here, you sit here, and then come from the right probably at different sections, and from the conjugate beam you find out the bending moment of that conjugate beam at those sections, and you are ready absolutely with the deformations or the deflections. So, these deflections are, once they are plotted, these deflections once they are plotted, it gives the actually the qualitative shape and the of the influence line diagram. Now, this can be actually if you apply unit load, this gives you the qualitative values also, or you can actually normalize as it is done for into the book. So, this can easily be visualized by saying that for statically determinate structure, now what is the difference with the statically determinate structure and the indeterminate structure? You can see this slide that the line of the influence line is a curved line, So, now that didn't happen into the statically determinate structure, because now you can recollect in statically determinate structure, once you removed certain action, it actually became unstable, and while you applied back that redundant reaction as a force component, that moved like a rigid body, You can see our old slides, and the class notes are here. I can show you once again that if you recollect if you recollect the influence line diagram for bending moment, if you introduce a hinge here, this part and this part will as a rigid body move if you apply moments, to actually like breaking it, if you do like that, it will take the shape. Two rigid bodies are moving, as if two rigid bodies are moving. Now, coming to our slides, here it is not. There is no two rigid body. It is still a deformable body, which when acted upon by a single force, come back to your slides quick. This slide. Yes. So, this is not like a rigid body, it still has restraint. So, if you put a unit load, it has to bend. So, the main difference you have for drawing the influence line diagram for indeterminate structures, they are curved, they are not straight lines, and that you need to remember. That is why we had to determine the deflections and at different intervals. We didn't have very easy points which we will join by straight line. No, that is why we needed to follow the curve. That is why we needed to divide into several parts. In fact, if required, we will divide into several more components and do that. So, I have nothing basically different to speak about the statically indeterminate structures. You can easily realize, if you are interested about the bending, the influence line diagram for the bending moment here, what you need to do for the structure, you release the bending moment into the structure by releasing it here. If you release it and put it back with a pair of unit moment, then definitely it deflects like this. At this point of time, this you may say that this will actually deflect straightway, and this will have a curve. And so, this is, but you see, we have destroyed the moment carrying capacity here. That is why it will be judicious to follow this line. and this is the influence line diagram. And for shear capacity also, we are allowing the shear to be happening, but we are not allowing any bending moment to happen. That is why if they are placed apart, a moment will act. But this deflected shape, it will give you the influence line diagram. Similarly, it is much easier to understand if you are interested about the middle portion, the reaction at B instead of reaction of A. You can remember, as in reaction of A it deflected like this, as in reaction of A it deflected like this, because A was going up. Now at B, if you put a unit load, it will definitely deflect like this. So this curved line is the influence line diagram qualitatively for the reaction at B. Similarly, if you have a moment at the support, you destroy the moment carrying capacity of the support and put unit loads, so they will individually actually be bent like this, and that is the influence line diagram for actually the bending moment at support. So I believe that that's it for the influence line diagram for the statically indeterminate structures, and we can see if there is a okay. So we can go for the next topic quickly. That is because it's a short topic, because we are going to understand qualitatively. That is why I can continue to that. So let us pause for a moment and think about that qualitative influence lines for building frames. What should we do? The building frames are actually highly indeterminate structures. You see that a building frame is what? There is a slab, there is a beam supporting the slabs and a column supporting the beams. So the load transfer mechanism is that the live load is there on the floor, and from the floor it is going to the beams, and from the beams it is to the columns. So that is how it is transferred. Now the beam column joint is usually rigid, even if sometimes it is possible to make it flexible. You may see the space truss type of construction. It is possible to make it flexible yet stable structure, but usually it is not. That rigidity you want, in fact, when there will be an earthquake or something, if one or two mechanisms are formed, the others will be holding the frame in position. So the stability will not be totally disturbed, and the structure, even if it is damaged due to the mechanism formed in one way or other, it will not be falling down because the mechanism is not complete. And some of the mechanisms, maybe suppose there are 6 degrees of freedom possible at a joint, maybe 2 are destroyed, the others will hold it into that position. So the building frames are highly indeterminate. Now let us examine that. If we are interested, why we will be interested about the building frames, I have already examined in the first day, that in the building frames 2 things can happen. The occupancy of the floor may be with a huge live load, there may be a crowd which is there. So that is a huge live load and overcrowding and overloading there. So I need to know that what are the conditions which makes certain members like the beams and columns vulnerable. To do that, I need to have the influence line diagrams of such building frames very quickly drawn on a qualitative basis sometimes, and sometimes quantitative basis. Let us examine how to draw qualitatively the influence line diagrams for plain building frames. None of the building frames are plain, but still if there is a symmetric arrangement, you can analyze the building frame with a symmetric load, with the symmetric load onto the building can be actually such, it can actually be divided to be acting onto the plane frame, and you can analyze that plane frame with without lateral restraint and get the conservative idea about the moments and the shears acting on different members. So in our particular your slide, we will demonstrate that how useful is the Muller-Breslau principle to draw the qualitative influence line for building frames using Muller-Breslau principle. So since building frames are subjected to bending moments predominantly, the location and distribution of the live loads which can have the maximum effects can readily be constructed using the Muller-Breslau principle. For example, we are showing a building frame and it is desired to determine the influence line for bending moments in a central girder at first floor level. Take an example that the bending moment in its central girder at first floor level. For this, a moment release is made in that girder, and the qualitative deflected shape of the entire frame can then be carefully examined. And we will see how that particular distorted figure and and the original figure of the frame, what area they enclose, and according to our idea whether it is positive and negative, it can give a fair idea about which are the portions of the building to be loaded to have maximum effect, such as the bending moment at that particular portion of the girder to be maximum or minimum, that minimum or negatively maximum. So, those are to be determined very easily. So, the panels which needs to be loaded to have maximum positive bending moment can readily be assessed, since the deflected shape also gives the qualitative influence line diagram. Yes, come to this point, let us examine. There are plenty of examples in any book related to say the same building frame, maybe somewhere some more stories are drawn. In fact, one will be in your assignment, so you can draw it yourself. So, correctly understand this. This is the building frame where the green colors is there. The green color is a deflected shape. See the black color frame. So, the black colored frame is the original frame. We are interested about where that C is written, the bending moment of the middle of this actually bending moment, the influence line for the bending the influence line diagram for bending moment at the midsection. So, obviously, midsection for a beam, it might be subjected to the highest sagging positive bending moment. That is why we are suspecting that should be examined. Yes, and now we are examining with actually the Muller-Breslau principle. Now, how to apply the Muller-Breslau principle to this frame is exactly the same we have applied to the beams and the trusses and also the indeterminate structures. So, this is also indeterminate structures, and now let us destroy the moment carrying capacity of the beam into that plane. So, the beam at this point no longer takes the bending moment here. So, to do that, I need to introduce a hinge, an internal hinge there. An internal hinge is a moment release support. Suppose this my hand is actually not both way, but one way it can release the bending moment. So, if somebody tries to bend my actually this hand this way, he will never be able to do that, because my hand here is already giving way that you can bend it no problem. Two rigid bodies, one is here, another is here, connected by an internal hinge, and that is how it will not resist bending moment this way. Of course, the muscles can resist the bending moment, I can become stiff. So, the stiffness of this beam can be increased, and there if somebody applies load, he will feel some resistance. But without that, with my hand, it is just a release like a internal hinge. So, here an internal hinge is formed. If it is formed, so then we will if it is formed, the internal hinge, then I can say that this portion should go up, but since this is a statically indeterminate structure, this joint, which is a beam column junction which is stiff, will not give way, and it will try to maintain the 90 degree with respect to the columns and the beams. So, if I have to rotate, because I have lifted this position, so this is the bent portion of the girder, this is the bent portion of the girder. If this is the bent portion of the girder, this here at the beam column junction, the whole thing need to actually rotate, the whole thing need to rotate, that is what it has done. So, its column has been tilted, its beam has been tilted down in one side, and this beam has gone up. To do that, it will have a deflected shape like this, and it will also bend the column there. Of course, we are drawing it in an exaggerated manner, and we are actually having a diagram for all the portions of the frames like this. If so, you can easily identify if this is, we say it's the sagging moment effect, because the moment you apply the unit load apply in the sagging direction, if this is positive, this will also be positive, this will also be positive. This is giving the qualitative influence line diagram for this frame, and it is immediately apparent if you explore that which part of the building frames should be loaded to have the maximum sagging bending moment here. Here is the answer, that you have this point where is the positive part, this point positive, this point positive. So, you load it here, here and here, you get the maximum. Also, it says since this is negative, you should not load it vertically downward. You may load it vertically upward if possible, but that is not discussed in a building frame. The building frames, the load is vertically down. That is why you should load here, 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 and as well keep this span and this span vacant for to have the maximum bending moment at C. If you load it here and here, then the bending moment will be balanced and you will not have the maximum sagging moment here. Of course, you will have some other effects like the column load will increase, that is different story. So, now going to the, so that is it, I have nothing to actually say. So, we have discussed what we have discussed here is that from the very beginning. Let me show you the slides once again. Yes, we started here today in the morning. Yes, yeah, that's there. Yes, day 3, session 5, influence line for indeterminate structures. Quickly show them the diagrams we have drawn today. I hope you have understood well the basics of that. There is no more complicacy. Once you understood that, you will at least be able to extend it to simple structures, simple indeterminate structures. Yes, come down, come down. So, now yeah, this is for the conjugate beam and one of the beam, and then this is the influence line, and then this is the other effects, and we extended it to the building frames. That is it. So, now going to the references, I have taken help, direct help, mostly from Professor Hippler's book and also Professor Wang's book, Professor Menon's book also very much, and Professor A.K. Jain. Many of the examples are from there. I have taken help of NPTEL course of IIT Kharagpur. I have a list. Can you please focus here? I thought in the morning that I must tell you about the other books which I have written in. I have many more books in myself. So, I have taken help of Li-Ten Wang's books, Professor N.C. Sinha's book, Professor Ramamutham's book. Lot of examples are there. B.C. Punmia's book and Professor Gupta, Pandit Gupta's book, C.S. Reddy's, Professor C.S. Reddy's book, and one book of Vaidyanathan and Perumal, where I have got a very interesting chapter on experimental determination of your the influence line diagram. Once again, the book here. So, this we have seen, and there are a lot of here are the authors. So, these are the old version, maybe there is a version. The other books which are the textbooks here, and this is Wang's book. I have taken help of Professor Jain's book is also there, and main textbook is Hippler's book here. So, I have shown you Professor Jain's book last time. So, these are the books we have shown and we have used. Professor A.K. Jain is a faculty in IIT Roorkee with whom he was my ex-colleague. So, I know that how it was actually done. So, now the thing is that that is it. What I say is that yesterday someone was asking me what is the good book for actually studying the influence line diagram of the trusses. I have seen all books, including the books just now I have mentioned of the professors. They are very, very elaborate. There are a lot of examples into this. If you have any of the books, those books, you will get lot many examples. But our textbooks and others, and in fact, I have named Alexander Chajes. One book I want to mention, Alexander Chajes, C-H-A-J-E-S. This book is not available easily. I have seen Professor Chajes's book in the library, in IIT library. It is extremely concise for the students, extremely concise for the student. Means if someone reads, he can finish off within 1 hour or so to at least grasp the fundamental. The textbook should be like that, that the student first get a glimpses of the main important things, then the details. The other books I have shown you, they are in very much great detail. You can if you can spend a lot of time, you will actually be with them, answering your questions. So, the thing is that I have one question from one student which is of interest, and he says KNMU John 1, it was, sir, we have a little problem about sign convention. Is it fixed, or we can have alternate sign convention also? So, let me elaborate on this issue. I believe this appears to be a very simple problem, but it is not. You see that you are studying some part of engineering in your bachelor degree, and then you will go for higher studies probably, or may not. Now, it is to be consistent throughout. Also, you are studying the rigid body mechanics first in the name of mechanics, then you are extending it to the strength of materials or the mechanics of materials, then you will go for the theory of elasticity in our higher studies, then you will extend it further to other kind of mechanics. So, the things should be ideally consistent. To do that, the type of notations which are actually consistent, if they are used from the very beginning, then it will be advantageous for you to understand the literature. So, to do that, I can draw one thing, that let us see that how we actually draw a 3D figure. So, if there is a 3D figure and if you are interested about the stress resultants, suppose this is the x direction, this is the y direction and this is the z direction. This is arbitrary to me, once again it is arbitrary to me. Now, usually the stresses which are perpendicular to in this direction, this we call sigma x x or is sigma x. This x is for the actually the plane on which it works and this is the direction. Now, there are two stresses into the positive 2 axis. Actually, there is a resultant stress here which we never mentioned in this plane, So, this is a plane perpendicular to x axis and you have the shear stresses tau and which is onto the plane x. This is the shear stress tau which is onto the plane x. The plane x means the plane which is normal to the x direction. Now, this is actually in y direction and this is in z direction. So, this is x x, this is x y and x z. I told you that this x z. So, if now this dimension is further extended, make the actually the member slender, you get your beam, and the moment which is actually acting about this axis, they will be acting as a bending moment, and this force which is the shearing force which will be acting as a shear force here. So, now looking from this side, if you draw the beam once again, you have a shear force here and a bending moment here. So, if you agree with the positive, so this is the famous right handed rule. So, it is a screw. So, if you unscrew it in this direction, you come out of it. So, this y is the positive direction. You can see it here. If you unscrew, you come out of this direction. This is positive. So, this ideally you should, if I consider a section here and consider this part, on the right of it actually right up, and this is positive. This is a sagging bending moment and this is the right up shear. Ideally, this is the sign convention you should follow to be consistent with further literature in higher studies or any other research materials. Now, for the students, now let us take an example of a beam. We are having a load here. So, this distance is A, this distance is B. So, your reaction here is P B by L if the total length is L, and this is P A by L. Now, if you are interested to determine the bending moment here at a section x, which is actually m x, now it is m x will be P B by L into x. Now, P B by L. Now, if I separate this out, this portion, if I separate it out and have a call out here, if I draw the portion of the beam which I have drawn, now here there is a force here P B by L, and I have the bending moment here. If I denote as positive, I should actually definitely denote the bending moment here as mx, but how about the shear? How about the shear? I have just learned I should have denoted it's right down, not it's right up, I should. But if I do that, if I do the opposite, if I left up right down, if I have right down shear as positive and then try to determine the things, what happens? Our shear diagram will be P B by L up, then P pushes it down, and then I go here and again P A by L pushes it up. So, considering at each section, I am drawing basically the load diagram and calling it a shear force diagram, calling it. So, positive shear comes for me when the actual load, which is the reactive force P B by L, which is acting on the left, it is left up. That is why our sign convention is positive for the shear is left up, right down. It is arbitrarily chosen. It is opposite to what we have discussed for the 3D entities here, but it is very convenient for the students here to assume that for bending moment I have the sagging positive which actually bends it like this. So, I should have the another color. So, it tries to bend it like this when it is bent, and this tries to distort it like this when it is left up, right down shear, and this if I take it positive. So, if I take it positive, then my shear forces. So, this shear force in the absence of bending moment will try to bend the beam like this, will try to bend the beam like this rhombic way. So, this is I say that if I isolate one of the members, it will be actually left up, right down positive shear. If I take this positive, then it becomes very easy for the students to visualize and quickly draw the shear force diagrams, and it is very intuitive and very natural. I am having a force, I am drawing it. So, basically what you are doing is the external force or the force itself you are drawing and calling it an internal stress resultant. So, as such it looks not so much comfortable, but it is absolutely okay if your sign convention is arbitrary. If your sign convention is arbitrary, who restricts me from assuming this to be and this to be the positive? Nothing, it is absolutely arbitrary. So, many of the books follow the earlier convention, many of the books follow this convention. I am following in my discussion, and if you draw the bending moment diagram, there is one more thing, you draw the positive thing on the upper side for the shear and the negative shear on the lower side of this thing. But for the bending moment, the positive is drawn onto the compression side. So, the beam will bend like this. So, that is why this is in compression and this is in tension. If that is so, I draw the bending moment actually on the compression side, just it is arbitrary, and many of the books do that. So, drawing the positive shear on the upward of the reference line and drawing the positive bending moment onto the compression side is absolutely arbitrary and should be acceptable to us. Now, to answer the queries to John that yes, the sign conventions are absolutely arbitrary, chosen by us, we are free to choose the other one. But being a student, I will advise strongly to you, it is it is unnecessary to create confusion with the sign conventions. Follow only one, it is arbitrary. There is no harm in sticking to a particular arbitrary sign convention. You are not going. So, the problem will be once you are brought up with a sign convention, it will have difficulty in following the other textbooks, or you may not like it. The textbook which does not follow your sign convention, you may not like it. For example, I will tell you that we are all familiar with the Cartesian coordinate system x and y. How about if we are following this from our school days, but what about this? This is x and this is y, nothing, there is absolutely no problem, we are not used of it. Anything drawn in this axis will not be, it is just the mirror image type of thing that we are not comfortable. So, this is also acceptable. This was developed with a positive increasing thing from our left hand to right hand and positive increasing thing from bottom to up as we read the map. So, that is how it has happened. And we are absolutely familiar with this, and that is why we are feeling comfortable. Now, yes, so you got your answer, it is absolutely arbitrary. Now, you get my advice, do not confuse with the sign convention, there is nothing to gain about the sign convention. If you are confused, follow with a single textbook which has been written with a particular sign convention. If you are brought up with that sign convention, no harm. You will later on, when you become expert with the topics, you will change your sign convention later, no problem. For me, it's either, I can read both the sign convention equally well, so there is no problem. Still, it will not be good in my class note if I follow two conventions and always mention that now I am following this, now I am following that. It's not good. I am following one sign convention, and for the comfort of the students, I am not deviating from the sign convention of my textbook. So, I have actually, this is my textbook, this is a textbook, I am following the sign conventions what is given here, and I may not like it sometimes, no problem, I have to go with one. One reason the student confuses the bending moment diagram and the influence line diagram is that bending moment diagram is taught first. That is one reason, but there is a genuine reason that the bending moment diagram is a spatial variation. Anything spatial variation, I can assume it is with respect to x axis something is varying. I can have the ordinate y axis, but indicating the variation over the length of the structure, but still saying that it is the variation at a particular point on the structure, that creates the problem. That creates the problem. I told you there is a way out, that the development of the influence line, it is convenient for the engineers. They found it most convenient and it is represented like that. Other way, what we could have done, suppose instead of the influence line, we could have thought that different section, I am taking different section on the beam, and each section of the beam I am indicating the values of the bending moment with a bar chart or some values as the unit load moves. So, as the unit load moves, this is the value here, as the unit load moves, this is the value here, and reading that bar chart type of thing, I could have devised some actually methodologies which will be conveniently replacing the influence line. I am telling that is not going to happen. The influence line is absolutely fine for the with the engineers. I am telling you what is the alternative. You will very soon realize that it is better to actually twist your reference. It is better to twist your reference. That means, better you be conversant with the idea that what I am seeing in my eyes is actually a variation at a single point. That is the problem. You see, the problem is that you can remember, if you can recall, I am using the same paper on the back side of it, or okay, let me have a fresh paper here. So, you can recollect that this is the beam. Okay. So, you have a load here. So, you have a reaction here, suppose P by 2, P by 2, I am putting the load. So, what is the shear force diagram according to our sign convention? It goes like this. It is the shear force diagram, positive shear and negative shear. So, it is P by 2, it is coming down by P, and then it is P by 2 negative. Now, what is the influence line diagram? You will find it like this, and not only that is negative, it is positive. Now, for that you have to explore that what is this positive, negative, negative, positive all about, and what is this shape and this shape all about. You must digest the fact that this is a spatial variation. This gives the shear force at different locations. So, if the question is asked, due to this load, what is the shear force at this point, this point, this point, this point, this point, this point, this diagram answers. Now, if the question is that what is the shear force here, if a unit load moves on it, then that is the answer. So, they are quite different. The problem is that they are drawn on the same spatial scale. So, I told you the alternative is not good, the alternative is no more better. The better you train your mind, to accept that this is the bending moment diagram itself as a spatial variation, and this is influence line diagram for the bending moment at a section. So, for another section you will this is not the bending moment, so this is the shear force, this is the shear force influence line diagram. So, you better train yourself, this is a shear force diagram. So, and this is the shear force influence line diagram. So, if you have told bending moment, that is unconsciously I have told, I have drawn the shear force diagram as well as the influence line diagram for the shear forces. So, I was concentrating on explanation, that is why it slipped from my mouth that it is the bending moment, but it is actually shear force bending moment diagram, shear force diagram itself, and this is the shear force influence line diagram for a particular point. For all other points, you will draw similarly the shear force diagram, influence line diagram for shear force, and then maybe trying to guess their envelope, which will be actually for the shear forces like this, and for the bending moment it will be actually having different kind of bending moment, and you will have a profile of the bending moment, and this will have an envelope of the shear force and envelope of the bend. I have not discussed this because these are not basics, these are derivative of that. Neither I have discussed in detail how the final maximum bending moment and shear force diagram should look like. That I have shown you yesterday one paper of Professor Ramamurtham's book, I think. So, now that those things are not basic. So, you have to digest that this is spatial variation, this is the variation in a particular location with the unit load moving. You better train your mind like that and be prepared for further answering the queries. So, this is I have given this assignment and also for some theoretical questions, and then there are certain difficult questions which cannot be set for the quiz. Those have been set in the and these are discussed in the class. These are discussed in the class, so you will be very comfortable. That if somebody was asking about the uniformly distributed middle, how to find out the area under the curve, those you explore through these questions. Those are assignments, and I hope that these assignments you will be doing after preparation, so there is no problem, and these are very standard, any book is having. So you then it goes to the qualitative shape of the different influence line diagram for statically determinate and statically indeterminate trusses, and also for frames, the portal frames which have indeterminacy and different kind and also the building portals. So these are the actually the and I have the solution, so which I will give to you. Now the proctored quiz, I cannot show you the proctored quiz questions. They will be coming as a surprise to you. So that your teachers will conduct. I have prepared the answers for the quizzes, everything. So they are quantitative and for the unit load and uniformly distributed load. So I believe that this should be good for you. So let me know that how do you feel about this course. What you better suggest, you be critical with this particular session. You tell me that how can we improve if I have to teach in future. What else you expect, and I can say that how I can actually try to incorporate. I have not taught many things, like I have not discussed about the floor loading. The floor loading is not easy. The cross girders, from there the longitudinal girders actually are taking the loads, then transferred to particular columns, and how to actually some of the girders are loaded at certain discrete points. So their influence are like the trusses, they are to be done separately. And also for the industrial cranes, their movements, the conveyors which is actually flexible but supported on rollers, they are different problems. There are many interesting problems with the influence line, but the main application will be in bridges. If you do not know the influence line, you have to learn it quickly before you attempt the bridge analysis, because the lot of live loads, and also if you follow good textbooks like Professor Victor's and others that about the bridges, you will readily understand that still the issue of the load has not resolved. So the IRC loads and others for the bridge, they will improve in future in description. So you have to incorporate them in their effects into your structures. If you know influence line, it will be very easy to do a first principle analysis, that whatever load is defined, and with the loading is slightly different than the standard, you definitely need the your influence line to explore what is the maximum, where it is maximum, and then you can have a computer program also to be written, and that is it. So that is how it will progress. So let me see any questions. Any suggestions for improvement for this, and any questions you can just discuss with me, and then we can have them actually discussed with all other colleagues and students. So everybody will be knowing, it will be good. And if you have felt that it was well understood, that also you let us know. So we will actually point out that it was good, but you can be critical also. You can say this part I could not follow much. Even a well delivered lecture, very slow lecture, perfectly understandable, is not sometimes going very well with students. Because of that, the background, different background, and the preparations you have, that makes the difference. The prerequisites, I have assumed many things that you know, maybe you are still not knowing that much well. You have studied it, you know to some extent. When times come, you will recapitulate or you learn it better way, but right now you cannot recollect in the class that yes, that conjugate beam I have done once, I have solved a few problems, but then after that I have forgotten. Like it happens, it is very natural, it is very natural. So like that, the influence line is somewhat advanced topic, but you have observed that there is nothing fundamentally very difficult. It is all about moment, shear, force, reactions, all these things, and geometry. So it cannot be a difficult concept wise. It's application wise very useful, but concept wise the things are not very great difficult. Yes, somebody has asked that our library section is not well equipped. So, can we have all this session in library? I believe that all the materials you should get. I am not sure, because that you have to make sure from the administrator. He or she will make you understand what you should get and what you should not. That is up to the QTP. But the materials I have delivered, you see what I have done. I have not prepared anything novel or anything very different from the existing textbook. Everything is there in detail and in the same way, and I have drawn my figures to convince the students that these are easy to draw, and this is the way one should draw in the class as well as the student should draw in the examination hall. That is why it is drawn. Nothing is shown to you which is difficult to actually perform, and it is the same in the book. If your library does not provide, you can have the textbook from any source and read them. So, nothing can prevent you from learning. I will be happy if the materials are made available to all of you. So, let me see any other question and feedback. So, you can also write that if it went well to you, that also you can I can share with all others here. I can share with all others here. Okay, that I will show you by this time one thing. Here you see Professor Hibbeler's book. I am opening because it is our textbook. All textbook starts like that. It is mainly this type of structures, the indeterminacy, and that internal loading means shear force and bending moment. Then the structural entities like cables, arcs, all these things are taught. After that, you can either actually start the influence line as it is given in this book as statically determinate, or you can postpone it till the last once all the deflections. Actually, the deflection is needed for statically indeterminate structures very much, and all the deflections and using energy methods and others are actually covered. You can have at the end the chapter of your influence line diagram is actually somewhat independent. The video, yeah, the chapter of influence line diagram is actually independent. You can it can be started later on. Yes, there is a behavior of frame to draw the bending moment diagram. Yes, there are two questions. So, there is one question from Snehal GHRCE, difficulty in understanding the behavior of frame to draw the bending moment diagrams. And the next question is from John again, KNMU. So, which is the best book for influence line diagram as per our syllabus? There are a lot of questions for the textbook. First I answer that. You see, it is not very comfortable for me. So, John, the thing is that we are a bit uncomfortable to directly prescribe a textbook. We cannot advertise for the textbook. I have shown you what is taught in the IIT Kharagpur. That's I have the right to show you in that way. So, it is not that I am promoting any book. I have shown you some books which are very concise, like Professor Hibbeler's book is very concise, and what is not available, I have shown you the name that is for your Professor Chajes, Alexander Chajes book, that is very concise. Professor Menon's book a bit elaborate, but still it is concise than many others. What I am telling you, and also Professor A.K. Jain's book is very concise, but that focuses on indeterminate structures. Determinate structures, there is another book which is also good. And Professor this Vaidyanathan Perumal, I have told you that is for experimental thing, you can look at it, very curious chapter is there. Now, the thing is, apart from that, I have shown you several other books. Now, I am only talking about the books which are very concise. So, if you talk to me, I will say that if you follow our textbook, then it will be easier for you to understand the propositions. It will be easier for you to understand the propositions. It is well explained within a very short wordings that what is happening and leaving all details aside. In fact, it is not given. That is good for the students. You have a limited time in the semester. Influence line diagram is one of the topics out of many. So, that is why we cannot spend probably apart from few hours, and that is why we need to be concise. If you later on refer to details, you can refer to the books I have shown later, the names. You can refer any of the books, you will find tons of informations there about the detailed analysis of many structures. So, that is how the things work. Okay. And one more, this somebody else was questioning that the difficulty in understanding behavior of frame to draw bending moment diagram. So, can I connect first to can I have the you can connect as well as you can show the slides also, isn't it? Yes. So, connect to GHRCE Snehal there. So, we can connect it here, I think. Hello, good morning. Yes, please, the question.
How to draw the bending moment diagram? Yeah. How to draw the bending moment diagram when for the influence line when the moment is occurring on the frame? That is the first question. Second question from the student side is how to draw the influence line diagram when moment is there on the beam.
Yes.
P moment is there. Yeah.
I think that probably the question is not, the topic is not well understood. First of all, definition of, let me speak, the definition of influence line diagram is that when the effect for which we are drawing a unit moment or a unit force when they are occurring. So, I have shown most of the example with a unit force. So, if you are interested, so we are moving a unit load because we were concentrating on the finding ultimately the effect of a series of concentrated loads or a uniformly distributed load which is acting vertically downward. We have not actually discussed what is the if we are interested about that when the load is applied itself is a moment, how do you get the effect? That's probably is a question. So, if that we have not discussed here, that is to be separately done, because for that you need to be ready with the unit moment effect and how the actually that the thing is that let us understand the basic. It is on the linear structure. We are going to use the superposition principle. If you go to our first few slides, what it discusses about that. Let us form the problem with a unit load moving, and when the actual load comes, we are ready with the ordinate of the influence line diagram. So, if you are exploring exclusively the effect of the moment occurring at different locations or a combination of moment onto the structures, and then if you are actually exploring that how can you concise the analysis through an influence line diagram, that is to be done separately. That is to be done separately. So, clearly understand what we have done. Our focus was on the structures where there is a lateral loading. The moment also is caused by that lateral loading. So, if you are now concentrating on that there is no lateral loading, I have a moment applied and I want to explore at a particular section what is the effect, then you have to just reformat the whole procedures for that moment. So, I think you will go for the unit moment there and the influence, but you see that the applications are you need to find out where such things will be actually applicable. So, our application is mainly with the bridges, the cranes, everywhere there is a transverse loading. So, the beam type of structures will be subject to bending moment and shear forces. We have formed the questions like that. So, the unit load moves on that. Okay. So, it's like that. Okay. So, any other question, please you can ask. Yeah. Any other question? Let me see.
You, sir.
Thank you very much for listening. Yeah, there was a question about the about let me first answer that difficulty in understanding behavior of frame to draw the bending moment diagram. I have not drawn the bending moment diagram really. I have drawn the influence line diagrams for bending moment. For drawing the bending moment diagram of a frame, you have two ways. Either you go for the approximate analysis, you know the approximate analysis for lateral load and the the vertical loadings. So, if there is a building frame, suppose there is a building frame, what is there? Suppose there is a building frame and they are actually fixed here, and then these are building frame fixed here. So, if there is a loading here, if you are interested about the bending moment in this beam, you can separate that out as a fixed. Suppose in an intermediate beam you take, that will be advantageous. Suppose take this beam which is fixed at both sides. Let us draw it. It will try to deform it like this. If it tries to deform, then there is a hogging moment here, there is a sagging moment here. So, you have a contraflexure point here. So, you can see that this particular problem is basically you have a fixed cantilever from both sides, and you are having a beam hanging with supports. Suppose this is a roller support and this is a pin support here, or this is the problem, and the live load is here and here as well. So, with that you can have an approximate analysis due to the vertical loading, or else if you consider the lateral load due to the wind and the earthquake and you reduce it to the nodal loading, then you can go for the cantilever method or the Portal method to draw the Portal method to draw the approximately the bending moment diagrams of that. But mind that for that it will be like this, and there will be assumptions that the inflection points occur to the midpoints or somewhere else you define, and like that you can have the linear variation of the approximate bending moment, and you can assume really the bending moment with this will really have a moment here and a curvature and then a inflection point in the middle. So, like that you can actually draw the bending moment diagram and the shear force diagram. If this is your question, I believe that I have answered that, but what I have drawn, if you go to my slide, can I see the old slides? Yeah. So, I talked about the application of the Mueller-Breslau principle to draw the the influence line diagram, not the bending moment diagram, the influence line diagram for the bending moment at a particular section. So, it says that if I load it here, I get a positive bending moment here. If I load it here, I get a positive bending moment here. If I load it here, I get a negative bending moment here. So, all are bending moments at this section, and then actually it is the influence line diagram. So, I am sure that if I have to have the maximum positive bending moment here, I must load the portions which are shaded with this deformed curve and the original curve, and that is what has been drawn here. So, loading any other place will effectively reduce the bending moments if there is a curvature present there. So, that's how it is. Now, suppose by chance there is an extension of this frame where the moment is actually released by internal hinges, then loading in this section will not affect this. So, that's how. So, now that's what we have drawn. So, one question is that the influence line diagram for bending moment as C is this, and the bending moment diagram of the particular bending moment diagram for the particular. So, this is a hogging bending moment. So, bending moment diagram for this structure will be this kind of variation for here, with this kind of variation, the positive and negative bending moment here for the live loads and for the imposed loads or the dead loads, and for the actually your lateral load it will be like this for columns and the beams. So, these are pure bending moment diagrams for the spatial variation due to a system of loads, not the variation at a particular point. Okay. So, so I hope that was understandable. Next question is that from RSCI VTC, that sir, is it possible to do any mini projects related to determinate and indeterminate structures? Yes, I have shown you that two things you can do. Either you can have an analytical or a numerical problem with computers, or theoretically done, or you can have the experimental determination of the qualitative shape or quantitative estimation of the influence line diagram for trusses and other type of structures in the laboratory by loading with a unit load. That is possible. Now, coming to the analytical front, even I have explored sometimes with students that suppose there is a bridge structure, how to load it to have the maximum this bending moment at certain points, considering actual practical loading scenario. If you have a videography of all the trucks and vehicles moving, you know the time instance how the occupancy of the bridge with vehicles. Do the analysis using the influence line diagram for different locations, bending moment and shear force, and this project can well be formed. Some of my students have already done that in a similar manner, but they worked on dynamics, but you can do a static projects very well, and very good projects you can form. You can take a practical bridge, and if you have any real data or a simulated data or an assumed data, you can analyze for a particular stream of vehicular loads how the sectional bending moment and shear force are varying. That you can do. So, this is the a practical project you can do either analytically or experimentally. You need to restrict to laboratory models mainly. It is very difficult for us to actually go to the actual bridge structures and do that, but practical engineers do that, and you need to read several books and reference and also papers. So, it will be a very interesting projects. I am sure these will be very interesting projects. So, it is there another question is from GHRC Snehal. Thanks sir, in our syllabus influence line diagram is for frames and beams with simple loading and moment. Yeah, it is for the moment comes from the loading itself, and we are the sum total effect we are actually assessing. So, the thing is that how long you can be with the students, and what are the maximum time the students can spare for this single topic. They have several more topics to actually cover in a syllabus, and more so because suppose in our time when I graduated more than 30 years ago. So, it was around 30 years ago. So, it was in 1988. So, it is 29 years ago, isn't it? So, at that time there was no computers here. So, we have all the projects manually done, all the bending moment, shear force for the entire building structure, 12 storied, manually handwritten, and for the even for influence lines and others we have done it manually. Now, there are several subjects also have grown, which are becoming day by day more important. So, the traditional learning part has shrunk to some extent. So, we have to be very concise, specific, and with very less time we have to teach the students. We have to restrict to very less examples and simpler examples. That is what we have done. So, I think it is all right if with a beam it is done well, and we can extend a little bit to frames, because the treatment for both the structures elaborately not possible. Truss is a bit easier. That is why if you include truss, because the bridges will be actually will have trusses. So, not knowing the influence line for trusses will have a disadvantage. I have included in the assignments as well as assignments mainly. So, I think it is a good idea to include the beam, just touch the frame to some extent, and then give one or two examples for statically determined truss they will be knowing, and that is it. Other things, floor girders, cranes, they are very difficult to be incorporated within a time limit. We do not do that. We advise the students to read whenever they are interested, or in future when they require it in practice. Yes, there is a question that sir, is it possible to share our problems with you after the end of all 3 sessions in future? You see, once we are tied up, we are already having common emails with your teachers, and the students can always communicate to us. In fact, it is not restricted to you, anybody can communicate and they communicate to us, but we are extremely busy with our teaching, consultancies, and also with the research and the research projects with a lot of project students of ours. We provide time for others, no problem. I will always suggest that your teachers are the best who are locally available and for you, and actually they should be consulted first, and we are always ready to cooperate and answer your queries every time. So, I am available after this interaction as well. So, that there is a from QTPD all our details are given. So, and anybody can contact. I will be very happy to answer. You should learn the most of any topic from a good textbook. The other things are supplementary. A video lecture, interaction with others are supplementary. The best way to learn anything is sit with the best textbook alone. And have a nice day. Thank you very much.